Ever wondered why an apple falls to the ground, or why planets dance around the sun? Let's dive into the core ideas of general relativity, starting from the basics, to help you understand why space-time is curved. Gravity is a fundamental phenomenon in the universe. It's the force that pulls any two objects closer together, whether it's an apple falling to the ground, the moon orbiting Earth, or Earth orbiting the sun. Many might think gravity depends solely on an object's mass. The larger the mass, the stronger the gravitational pull. In Newton's theory, this makes sense. His laws of motion perfectly calculate things like the time it takes for an apple to fall, or the orbit of planets around the sun. But gravity isn't exactly a force in the traditional sense. Take a satellite falling toward Earth, for example. If gravity were just a force, the satellite would fall directly toward Earth's center. In reality, its path shifts slightly due to Earth's rotation, creating a deviation. Another example is Mercury's orbit around the Sun. Over time, its orbit shifts in a way that Newton's laws can't fully explain. This suggests gravity isn't just about masses pulling each other. Instead, it might be an effect of space-time itself being curved. The foundation of general relativity rests on the equivalence principle. Imagine you're in a sealed box in deep space, far from any galaxies, so we can ignore their gravitational influence. You're holding a ball and you're weightless. If you let go of the ball, it floats in place. Now, suppose the box's base has a thruster that ignites, pushing the box upward at a constant acceleration. You'd feel a force pulling you towards the box's floor, and the ball would fall toward it at the same rate. If that acceleration is 9.81 meters per second squared, it feels exactly like standing on Earth's surface. The pull you feel, and the ball's fall, would be indistinguishable from Earth's gravity. You couldn't tell whether you're standing still on Earth or accelerating through space at 981 meters per second squared. Inside the box, you might think you're feeling Earth's gravity. But someone outside would see the box accelerating upward, hitting you and the ball. There's no Earth pulling you, just the box's motion. Now, let's say the thruster stops, and you're weightless again. You turn on a flashlight, aiming the beam at a point on the box's right wall. If the thruster restarts, accelerating the box upward, the light beam appears to curve downward, landing below your target. Inside, you see a curved path. Outside, an observer sees the light moving straight, but the box's acceleration makes it seem curved to you. So, who's right? General relativity says both are correct. Inside, you think you're on Earth, feeling gravity. Outside, the observer knows the box's acceleration creates the illusion of gravity. This shows gravity can be equivalent to acceleration. The greater an object's mass, the stronger the equivalent acceleration. Now, let's explore why curved light paths make time slow down. In the accelerating box, you see light bending, meaning its path is longer. Outside, the light appears straight. According to the principle that light speed is constant, both observers measure the same speed. But inside, the light's longer path means it takes more time to travel. Since time equals distance divided by speed, a longer path with constant speed means time inside the box slows relative to outside. The more massive an object, like a black hole, the greater its equivalent acceleration. This causes more significant light bending, longer paths, and slower time. An apple moving in a straight line through space, when near Earth, appears to follow a curved path due to gravity. You could say Earth's gravity acts like an acceleration, bending the apple's path. Or you could say Earth curves the surrounding spacetime, forcing the apple to move along a curved trajectory. Objects curve spacetime. The greater the mass, the more spacetime curves, leading to longer paths and slower time. In short, the larger an object's mass, the more it warps spacetime, and the slower time flows around it. That's the essence of general relativity. It's fascinating how gravity shapes spacetime, isn't it? Hope this helped make things clearer. If you enjoyed this, please subscribe to my channel for more dives into the universe's big ideas. Stay curious, and let's explore more soon.